Our next unit is going to be on velocity and acceleration, and we're going to start our first lesson on velocity. We're going to look at speed and velocity. And so in this unit, we're going to look at speed versus velocity, what the difference is and what the same, how these work as far as what's different and what's the same about these two concepts. We're going to look at instantaneous versus average speed, and we're going to look at how to calculate speeds, to do speed calculations. And so those are going to be the things we're going to look at here. Going forward, speed versus velocity. Let's define velocity first. First thing we've got here is that an object's velocity is the rate of change of an object's position. That is its displacement. So we have sort of a picture down here at the bottom. So we have, in this case, some object that starts off at point A down here and ends up at point B. And so when we're talking about the displacement of an object, we're talking about basically the straight line distance between where it starts and where it ends. And so in this case, the displacement of this object, which takes this path that's drawn on here, and so it goes from point A to point B along this curved path. The displacement is the straight line distance between those 2 points. And so that distance right there, whatever that is basically going to be the displacement of the object. So the velocity, v, right up here, is equal to the displacement d over the time t. And so one thing to note here is that this displacement is a vector. That's the reason why it has a little vector symbol sort of up top right there, little arrow denoting that distance is a vector, that displacement's a vector, because to go from A to B is to go a certain distance along this line here, but I could go that same distance somewhere else. I could go that same distance, say, somewhere over here to some other point over here. That this is not the same displacement right here as is the one from A to B that we have on the screen. The direction matters when you're talking about displacement. Just like, you know, if you were told to move a dish from the table to the sink, it's a certain distance. You're displacing that dish from the table to the sink. If you were to displace the dish by the same distance into the trash can, that would not be the same thing. Even though the distances are the same, the displacements are different because displacement is also position oriented. It doesn't matter how far you do it necessarily. Well, it does matter how far you do it, but it also matters which direction. And so since the displacement right here is a vector, then it means the velocity must also be a vector. And so an object's velocity is how quickly that displacement is changing, and therefore, and since displacement has a direction, then velocity also has a direction. So it is a vector quantity, so it has most magnitude and direction. So let's take, for example, let's say that in this case is this displacement between A and B is going to be, let's say it's going to be 10 meters. Now, the displacement may be 10 meters. That doesn't necessarily mean that the path that took us 10 meters. It's possible that this path that goes along here is instead 20 meters. But for velocity's sake, we really don't care about what the path length is. That's really not what we're interested in. We're interested in this displacement, this straight line distance. So let's say that it goes this displacement from A to B, 10 meters, and let's say to do this that it takes 5 seconds. To go ahead and do this here. So if I wanted to find the velocity of this object, then I would say velocity is equal to displacement, which is 10 meters, over the time, which is 5 seconds down here. And so as a result, I would end up with a magnitude of my velocity of 10 divided by 5 is just equal to 2 units are going to be meters per second right there. Now, I'm not done yet because this is a velocity. And so the other thing I would need to know is to get sort of my final value on this is I would need to know what direction that's in. And so I need to go ahead and find what this angle right here that goes between that. Now, right now I don't really have enough information to do it. We know it's going to be somewhere between 90 and 180 degrees for the heading on that. But so my final answer would be that in this case, that this would be 2 meters per second at some heading that we really don't have the ability to figure out right now based on the information here. But this is basically what velocity is. Velocity takes direction into account, and it doesn't care about path. It only cares about where you started and where you ended. So let's move forward here and look a little bit at speed. An object's speed is the magnitude of the rate of change in an object's position, and that is its path. Speed doesn't care about displacement. It doesn't usually care about where you started and where you ended. It only cares about how you got there. And so whenever we're talking about speed, is that we're talking about this path right here. We don't care about the total distance in the sense of where you started, where you ended. We only care about, in this case, we said it was 20 meters for this particular path. We care about the path that you took. And so the definition of speed, and speed Sometimes you will see this as being s as its variable right here, but most of the time it actually will be just v again. You sort of have to look at the context of the problem to see whether or not v is a variable for velocity or whether v is a variable for speed. I sort of look at what the question asks. So velocity, or speed in this case, speed is equal to distance over time. And in this case, this distance right here is going to be the path, not the displacement, but the path. T is still time, the same as it was before. And this is basically what you have for speed. Now, speed is a scalar. It doesn't matter what direction it is. When your car says you're going 45 miles per hour, it doesn't say 45 miles per hour north. That's not part of what you're measuring here. You have a speedometer, measure speed, not velocity. And so speed's a scalar, and it is dependent on the path that's taken. And so in our previous example, we had 20 meters was the path length, even though it's only 10 meters directly between A and B. We said that it took 5 seconds. So to find the speed, we'd say that speed is equal to the distance, in this case the path length, 20 meters, divided by the time, in this case 5 seconds. So 20 divided by 5 here, that we're going to get a speed of 4 meters per second. Don't have to worry about direction. Speed doesn't care about direction. Speed only cares about the path that you take. Now, note that this does give us sometimes some weird results, these differences between speed and velocity. If I were to walk 10 meters one direction and then 10 meters back to where I started, and let's say that it takes me to do that 10 seconds, I've walked a total distance of 20 meters. And so my path length is 20 meters, and so to find the speed, I would say 20 meters divided by 10 seconds the time, and that would give me that I've been going at a speed of 2 meters per second. If I were asking what the velocity was, though, what I would basically say is that where did I start and where did I end? Well, I walked 10 meters, and then I walked 10 meters back to where I started. My total change in position, my displacement, was 0 because I started where I ended. And so as a result, my velocity in that case would be 0 meters per second, because the fact that my displacement was 0 is that, just remember that velocity only cares about where you start, where you end, doesn't care how you got there. Speed does care about where you, basically not only where you start and where you end, but also how you got there as far as setting that up. And velocity has a direction to it because it's a vector. Speed is just a scalar. It just has a value. So let's move forward here and look a little bit more at speed. Let's see if my computer will listen to me. There we are. So we've got an example here, speed versus velocity. Suppose we have a man who walks on an equilateral triangle from point A to point B and then to point C. And the trip takes 30 seconds. And so he started off at point A here, and he walks first to point B, and then he walks to point C down here. And that's where he ends up. So the question is, first thing, what is the man's speed? Well, remember, speed cares about path. And the path that he took from A to B took 6 meters, then B to C took another 6 meters. And so to find his speed, his distance, that is the path length he took, is going to be 12 meters. Divided by the time it was, and we're told that was 30 seconds. And so we had 30 seconds. And so in this case, we take 12 meters divided by 30 seconds, and that is going to give us 0.4 meters per second. So that right there is going to be our speed. It worries about the path we take. Now, second question is, what is the man's velocity? So for velocity, we only care about displacement, where he started at A and then where he ended at C. And so that length is just going across here. Even though he didn't walk directly from A to C, we only care about the displacement, where he started, where he ended. And so to find the velocity, we would say in this case that the displacement is going to be 6 meters divided by the time, which is 30 seconds. And so we go ahead and once again divide this out. We would say that 6 meters divided by 30 seconds gives us 0.2. So 0.2 meters per second. But since velocity is a vector, we also need to know direction. In this case, he went from A to C. In this direction, that's going to be at a heading of 90 degrees. And so this would be at 90 degrees to find what our velocity is. And so that's how you would work out two separate speed versus velocity problems. Same circumstances, but how we have a difference between our velocity, which is a vector, and our speed, which is a scalar. And so how those work here. So let's move on a little bit. if once again it'll let me move on a little bit. There we are. All right. So let's look at a little bit of instantaneous speed versus average speed. So what we have here is sort of on the left side is a graph of displacement versus time. And so in this case, let's assume the object is moving in a straight line. And what we can see is that it starts off at a displacement at point A of 1 meter. It ends up at a displacement of 5 meters later on here at point B. And so we have that. We know that point A was at 1 second. Point B happened 10 seconds later at 11 seconds here. And so this is what we have right here. So basically this object is moving, and so it's changing its displacement, and we can see this graph of how it changes displacement as a function of time. Now, first thing we've got here. If we have a graph like this, this sort of gives us an idea of how speed works. We can sort of see how this works because on a displacement versus time graph, the object's speed is the slope of the graph. Now, if you think about it, slope is rise over run. In this case, the rise is the displacement, and so then if I look at the slope, it would be displacement over time, and displacement over time is basically the magnitude of velocity. And so the magnitude of velocity is basically speed. If we basically have something where we don't have to worry about the difference between if it goes in a straight line, and so the displacement and the path length are the same thing. And so basically we can find that if we can find the slope, we can find the speed. So let's take one particular point on this graph. Let's say we're going to look at this point right here, and I ask you what is the speed at that point. So if it is the case that the speed is the graph's slope, then I would basically want to find what the slope is at this point right here. It's sort of the tangent line that connects to that graph at that point. And so if I knew what the slope of that line was, that would tell me what the speed is. But I want you to look at this. If we were to pick a different point, let's say instead of picking that point right here, we're going to move down a little bit, or I can move up a little bit, and I'm going to pick this point right here. If I drew a tangent line through that point, it has a very different slope than the point that was earlier, the red line that goes with the red point on our graph. And so at 4 seconds where the red one was, we have a much steeper slope and therefore a much higher speed than we do at the green point at 9 seconds later on. The reason why is if you pick the tangent slope, the exact slope at any one point, this is going to give you what's called the instantaneous speed, the speed at that particular time. And if you have an object which is accelerating, which we'll get to later, that is the speed is changing, then you will have different speeds at different times. This instantaneous speed is what your speedometer in your car measures. It says, at this particular point in time, how fast is my car going? The problem you run into with instantaneous speed is unless you either have a way of measuring it directly, like your car speedometer, or unless you've basically taken some calculus, in which case that what you can find is if you have a graph like this, for those of you who know your little calculus here, if you take the derivative of that graph at any point, that will give you the slope of the graph, and so that would give you the speed. So if you have a function of distance versus time, the derivative of that function would give you the speed, which if you haven't taken calculus, don't worry about that. That won't be necessary for this class, but for those of you who have, that's just a little bit of a hint as to how this works. But if you don't have calculus, and if you don't have a method to measure it directly, it's relatively difficult to find the speed at any one particular time, because our normal way of finding speed is by distance over time. And if I pick one particular point on a graph, well, it's not changing its distance at that one point, and it's not changing its time at that one point. And so I can't find it using my normal distance or displacement over time equation. Now, what I could do is I could say I'm going to pick point A and I'm going to pick point B right up here, and instead of basically doing a slope at any one point, I'm basically going to take effectively sort of like the chord that goes across here, a line that connects 2 points on the graph. Now for that, I could figure out the speed, because I could say, you know, what I've got here is that speed is distance over time, or displacement over time. And so for this right here, I could say that the displacement, it goes from 1 to 5, that's a displacement of 4 meters, divided by, that should be a 4, I don't know why it's cutting me off here, but that's a 4 meters, divided by the time, it goes from 1 second to 11 seconds, that's 10 seconds. for my time here, and so the speed I'm going to get here is simply going to be 0.4 meters per second. And so that speed right there, I can do that calculation pretty easily. That slope, the slope of a line connecting any 2 points on a graph of displacement versus time, is called the average speed. This is a speed that is a little easier to calculate using the methods that are typically algebraic methods, let's say, just only algebraic methods, no calculus. Because if you can know what the original distance is, and you know what the final distance is, you know what the original time is, you know what the final time is, or you know simply the change in distance and the change in time, you can manage to find an average speed. It is basically the mean speed over that time. If we were to take all of those little slope lines, the red and green slopes, at all the different points along this graph and average them together, we would find that it comes out at the same slope as this blue line, as this chord that connects A to B. And so whenever we're setting this up, we need to keep in mind that there are two different types of speeds that we can talk about. We can talk about instantaneous speed, the speed right now, and we can talk about the average speed, the speed over either the whole trip or over some segment of the whole trip. And so those are two things we want to keep in mind moving forward. For this class, most of the time we talk about speed, we're going to be describing average speed, simply because based on the mathematical tools that most of us have available right now, that's going to be the most accessible. So let's go on and take a little look at how we might do something like this. So let's start off with a basic question. A car travels 145 miles in 3.5 hours. The question is, what is the car's average speed? And so in this case right here, we know that our equation is that speed is equal to distance or displacement over time. And so in this case, the distance it travels is 145 miles over the time, which is 3.5 hours. And so in doing this, once again, take out your calculators, and we would say 145 miles divided by 3.5 hours gives us a speed of 41.42, which in this case can be rounded just to 41 based on significant figures here. So just 41 miles per hour. And so this right here would be the car's average speed. Now, was it necessarily going 41 the whole time? Not necessarily. This car may have hit stoplights along the way. It's sped up, slowed down. It may have gone through speed traps and through small towns, and it may have gone through wide open interstates. But we know that since it took 145 miles in 3.5 hours, its average speed over this trip, or this segment of the trip, was 41 miles an hour. So, what's going on? Next question. After traveling the 145 miles, the car drives the next 55 miles at 60 miles per hour. What is the average speed for the trip? So in this case, basically what we have a car which is taking two segments. One segment which is basically 145 miles in 3.5 hours at a speed of 41 miles an hour, what we saw in the first problem, and then a second segment where they're driving 55 miles at 60 miles an hour. Usually in these cases, the best thing to do is to sort of set up a bit of a table. And so we have, if you look at this, sort of a before section. This is where we're going to call this part 1 of the trip. We have another section which is going to be sort of part 2, and we have sort of a total section of the trip, total or an average section. And what we're going to look at is we're going to look at basically what the distance is for each of these three, what the time is for each of these three, and what the velocity or the speed is, the speed for each of these three. And so let's look at this first section. This first section is the one that's right up here. And so for this one, it says the car travels 145 miles. So we know that the distance on this one is 145 miles. Technically miles in here. See if I can fit it in there without squeezing everything out of the way. We know the time for this one is 3.5 hours. Okay. And we know that the speed, we already figured that out, was 41 miles per hour. Miles per hour. Okay. Now, do we know anything else about the second section of the trip? Well, it says the car travels the next 55 miles at 60 miles an hour. So we know the second section of the trip was 55 miles. We know that the velocity for the second section of the trip was 60 miles an hour. Now, based on this, the question is, what's the average speed of the trip? And so we're looking for this. It's not really a total speed. It's in the total category. It's really an average speed. If you take the total distance and the total time, that will give you the average speed. And so we're looking for that one right there. And so the key is on these is that if we take the distance for the first section and the distance for the second section, if we want to get the total, we just have to add those up. So 145 miles plus 55 miles is right at 200 miles. So we know our total distance is 200. For time, we can't find the total time because we're missing that second time, the time for the second part of the trip. But what we can do is we know that there's a relationship between the distance on the second part of the trip and the speed on the second part of the trip. And that's that the speed is equal to distance over time. And so for this, what we can basically do is we can say that the speed, which is 60, is equal to the distance, which is 55, over the time. And so basically, so I'll multiply the t up on both sides, so we get 60t is equal to 55. Divide both sides by 60, and we get that the time for the second part would be 55/60ths, which is 55 divided by 60, ends up being 0.91666. So this would be 0.917, really. And so our total distance here would be basically, or total time would be 3.5 hours plus that 0.9166666. So we add those two up and we get 4.41. 7, really, 66666 afterwards. And so that's our time. So we know the total number of hours for this whole trip. Well, now we know the total distance that they go, the total time they go, and using those two things, we can use that to find the total speed that's here. And so, because we know that speed is equal to distance over time, and so the speed is equal to distance, 200 miles, divided by the total time, 4.417 or 1666666 hours. And so whenever we do that, we would end up with a speed of 45.28. And so this is significant figure-wise. This is going to end up at 45. And so our final answer here is we have 45 miles per hour is going to be basically the average speed for the whole trip. And so this is how you would work out a problem like this, as they went from 41 miles an hour to 45 miles per hour for the whole trip. And so 45 is our final one right there. And so that's how you basically use sort of a table to figure out what the average speed is for a trip whenever you're breaking into two segments so that you go different speeds. So let's try another problem. All right. So a bicyclist has a goal of averaging 10 meters per second for his morning 10-kilometer route. If he pedals at 8 meters per second for the first 6 kilometers, how fast must he ride for the remainder of the trip? That is to meet his 10 meter per second goal. And so this is also a case where we have sort of two sections to this. He has the first section, which is 6 kilometers, where he goes at 8 meters per second, and the second section, which is obviously 4 kilometers, where he travels at a faster rate to bring his average up to 10. And then we have a total, which should average up to 10. So let's set this up again. So we have, our beginning section, our second section, and our total. And so we'll look at those three. We have our distance, our time, and our velocity right here. And so for the first section, we say that he goes at a rate of 8 meters per second, and it's for a distance of 6 kilometers. We don't know the time it takes. We know for the second part, we know for the distance that the total distance is 10 kilometers. And we know that he wants his total speed to be 10 meters per second. Now, we got this set up. Let's double check our units to make sure our units work out here. In this case right here, the 8 is in meters per second. The 6 is in kilometers. And so those don't quite match up because we have meters for one, kilometers for the other one. So we're going to change this 6 meters, the 6 kilometers, to 6,000 meters. That way, we've got this sort of matches up here. And so this will change from 10 kilometers to 10,000 meters. That way our distance units are in the same type of thing. Now, if this is true, what we've got set up here so far, we know that the distance traveled in the second section has to be 4 kilometers or 4,000 meters. So we've got that set up here. The next thing that we can sort of find here is that we can find the time of that first section because we know they go a distance of 6,000 meters at a velocity of 8 meters per second. And so we'd set this up and we'd say that the velocity, 8 meters per second, is equal to the distance, 6,000 over the time. And so if we go ahead and solve this for time, multiply t up on both sides, and so we take 6,000 divided by 8. And so in doing so, we get a time of 750 seconds. So we get 750 seconds right in here for the time. That is seconds. Okay, for this one. We can also find the time for the total because we know the speed that he wants to end up at, which is 10 meters per second. We know the distance he travels, which is 10,000. And so for that one, we'd say 10 is equal to the distance, 10,000 over time. And so once again, we multiply the t up. And so we do 10,000 divided by 10, which is just going to give you 1,000. Okay? Now that we know the time for the first section and the total time, we can find the time for the second section, which has to be 250 seconds. Now, since we know both the distance for the second section, 4,000, and the time for the second section, 250, we can find the speed for that second section, how fast he has to go for the remainder of the trip. And so we know the distance is 4,000 meters. We know the time is 250 seconds. That's 4,000 meters, 250 seconds. And so then we get a speed of 4,000 divided by 250. And so we end up with 16 meters per second. And so this is a speed, so we don't have to worry about direction here. Technically, we probably ought to round this to 1 second figure because we have 8 meters per second and 6 kilometers. And so this would actually, final answer would be 20 meters per second. Of course, in reality, it's going to be closer to 16. If these are exactly 8 and exactly 6, and this is exactly 10, and that's exactly 10, this would end up being 16. But basically, this is what we've got here. That's how fast he has to go to basically complete his 10-kilometer trip at an average of 10 meters per second. All right. So let's go to one that's a little more complex here. Runner has 15 minutes to run up a long hill and back down again and get back to where she started. If she runs uphill at 7 miles per hour and downhill at 12 miles per hour, makes sense. How far can she run uphill and make it back in time? And so this is a very long hill. Is that, you know, it's for our purposes here, it's indefinitely long. She can run up it as long as she wants to or as far as she wants to. But if she runs too far, she can't make it back in time. And so we want to find how much distance can she run up the hill before she has to turn around and come back to make it back to time, make it back to where she started in that 15 minutes. So we do have two sections that are in here, and so we're going to set up our table just the way we did before. We have, you know, section 1, section 2, and the total. And we have a distance, of time, and a velocity for these. And so let's see what we know. Well, let's see. We know that she has 15 minutes, so her total time is 15 minutes. Now, since we're in miles per hour for both of these, let's convert that into hours. So 15 minutes is a quarter hour. So 0.25 hours is going to be the total time. Let's see. She runs uphill at 7 miles per hour. So that's the first section. And so her velocity to start with is 7 miles per hour. Then downhill at 12 miles per hour. So we know the downhill speed is 12 mph. Okay. And, well, that's about it. Doesn't look like we have a whole lot of information. We have the velocities at the beginning, the first section and the second section, but you can't just average velocities, add velocities together, get an average velocity. You can't average them together because you're not necessarily going the same time in both cases. In fact, we actually know you won't go the same time. She's going to run for a longer time uphill than she will back downhill because she'll cover that same distance back to where she started in less time. So whenever you don't have enough information like this, what you basically have to do is you're going to have to sort of set up some variables on this. So let's say that for this distance, this first distance here, that she travels some distance d. So we're just going to call it d. Now what about for the second section? Well, if you think about it, that the distance that she travels on the second section is basically the same distance she traveled in the first section. She ran uphill one distance. She'll run the same distance back downhill from where she turns around back to where she started. And so this is also d right here. Now let's look at time. For the first section, we don't know how long she runs for that time, and so we're going to have to call that t right here. Now, for the second section, though, we also don't know how long she runs for, but we know that if we take the time for the first section and add it to the time for the second section, we will get a quarter hour. And so by doing that, we can say that this time for the second section is the difference between the time for the first section and the quarter hour. And so we would say that this time right here is simply going to be 0.25 minus t. And so that variable version, that is a 5 right there, is basically going to tell us what the time is for that second section. Now that we have all of these here, we know that the total time is going to be 2d, and then we can sort of set up for the rest of this. But if we look at these two pieces we've got here, for the first section and the second section, is that we can make equations out of both of them. Now, those two equations that we make up will end up having variables. It'll have two variables. It'll have d, and they'll both have t. But since we have two variables and two equations, we can basically do a substitution. And so let's write out the equation for the first case. We know that the speed is 7 equals the distance d over the time t. For the second one, we know that the speed is 12 equals the distance d over the time of 0.25 minus 5 minus t, like that. So we can rearrange our first equation right up here because we multiply t on both sides, and by doing that we're going to get that the distance is equal to 7t, like this. Since this distance right here and this distance right here are the same distance, we can rewrite this equation down here as 12 is equal to d, which is 7t, over 0.25 minus t, like that. Multiply this bottom section up, so 12 times 0.25 minus t, 12 times 0.25 is simply 3. 3 minus 12t, when we multiply those up, is equal to 7t. So we're going to add 12t to both sides, so we get 3 is equal to 19t. Divide both sides by 19. And so when we do this, we're going to get the time, t, is going to be equal to whatever 3/19 is, which I cannot do in my head. So we'll try 3 divided by 19, and we end up with 0.1578. Okay, that is hours, which makes sense. It is less than 0.25, which is what we'd expect. And if we know what t is, then we can find d, because our original equation was that we had 7 is equal to d, which we don't know, over the time, which we just figured out over t. From our original equation right up here, which was I'll put the whole thing here, 15789, 4737 if you do the whole thing. So we solve for d, we multiply up that decimal in the bottom, 0.15789 times 7. And so to get this, I get a distance of 1.105 miles. And so 1.1 miles. Significant figure-wise, our final answer, since we had one significant figure on this guy right here, would be simply that she would have to go a distance of 1 mile before she turned around. And so she'd run up a mile up the hill, run back, and if she did that, she would make it back in 15 minutes if she runs uphill at 7 and downhill at 12. This is how you basically would set up a substitution problem for a velocity equation. Basic strategy works the same as before. Set up your before, set up your after, and then put in variables if you don't know what the values are. And you can then set up equations with that, substitute one equation into the other one, or sometimes substitute one equation into several other equations. It's quite possible to end up with a situation like this where you have more than two variables and more than two equations. But that's basically just straight up algebra once you get there to solve for your final answer.